Okay, so yeah, welcome everybody to today's seminar on automorphic forms. So it's a pleasure to have Naomi Sweeting from Princeton University, and she will talk about the arithmetic of Fourier coefficients of Gan-Gurevich lifts on G2. So Naomi, please.
Okay, yeah, thank you for having me. And let me also say, feel free to interrupt me with questions during the talk. I know it can be a little awkward on Zoom, but I'm very happy to stop for questions. Okay, also everything I'm going to say in this talk today is joint work with Petar Bakic, Alex Hiroa, and Daniel Lee Huerta. Okay, so with that said, I want to start with some very general kind of motivation. So if you have any automorphic representation of a reductive group, of course, you can break it up as a restricted tensor product of local representations at every place. But not all of these places are on the same footing. And in particular, the Archimedean place plays a special role. So imagine we're over Q, for instance. So the Archimedean component, pi infinity of this representation, determines sort of by itself how arithmetic the automorphic representation as a whole will be. So let me give sort of a brief example of this. So the classic example would be the holomorphic discrete series representations, for instance, on the group SL2. So the classical modular forms on the upper half plane give rise to automorphic representations of SL2 or GL2, whose Archimedean component is a holomorphic discrete series. And if you have a different Archimedean component, like a principal series or something, those would correspond to things like Moss forms, which are less arithmetic in nature. And this story is not specific to SL2. So similar things happen for any group with a Shimura datum, so such as symplectic groups or unitary groups. And the reason, or one of the reasons this is so, has to do with the theory of Shimura varieties. Automorphic representations with holomorphic discrete series Archimedean parts are very closely related to algebraic geometry. And you can use this relationship to study them from an arithmetic perspective. You can do things like construct their Galois representations, study their arithmetic properties of their Fourier expansions, and many things along those lines. But this story is not fully general, in that not every group has holomorphic discrete series representations. When you do not have holomorphic discrete series, it's sort of reasonable to ask which pi infinity are the most arithmetic ones, if any. So this talk is about the group G2. So G2 does not have a Shimura datum. It does not have any holomorphic discrete series. And yet, somewhat surprisingly, perhaps, it has still a very distinguished class of discrete series called the quaternionic discrete series representations, which empirically appear to be the most arithmetic Archimedean representations that exist of the group G2. So these are indexed by weights, so they're called pi sub k, indexed by a weight k at least 2. And if k equals 1, there's a limit of discrete series representation, just like there is in the classical modular form setting. So if we want to sort of focus in on the quaternionic discrete series automorphic representations, it makes sense to make the following definition, that an automorphic form on the group G2 is called a quaternionic modular form of some weight if, when you kind of look at its span under the action of the real points of the group, the G2R representation it generates is this quaternionic discrete series pi sub k. And moreover, that you also want, under the maximal compact of the group, you want phi to generate the lowest k type. So this is analogous to the situation for classical modular forms, where you can translate the classical theory into sort of these special automorphic forms where they generate sort of the right representation and they have the right k type. And you can also make this more explicit. So Aaron Pollack has a definition of quaternionic modular forms that really writes down what this literally means in terms of a differential equation that phi has to satisfy in some sort of how it acts under the action of the maximal compact. Okay, so that's the definition we'll be using for this talk. And a sort of basic fact to know about these is that they have a very robust theory of Fourier expansions. And in this theory, the Fourier coefficients, which I'll write as C sub A of phi, are indexed by totally real cubic rings. And if you know all the Fourier coefficients, you know phi. So this is similar again to the situation for classical modular forms, where if you know all of the Fourier coefficients, then you kind of know the Q expansion, and you've essentially written down the modular form. Now, this notion of totally real cubic rings, in case it's not so familiar, this just means a ring that's free of rank 3 as a abelian group, and as a ring, if you tensor it up to R, it becomes R cubed. So the basic examples to keep in mind here would be A is Z cubed with the natural multiplication, or for instance, A could be the ring of integers in a totally real cubic field over the rationals. And of course, you could also have A be something like a subring of a totally real cubic field, an order in a totally real cubic field. So these are the objects that you should think of as indexing the Fourier coefficients. However, in order to not have too many lies in this talk, I want to put an asterisk here that this story is actually only strictly true if the modular form you're looking at has some kind of nice level structure. So in the classical picture, you're probably familiar with the fact that sort of if you have like a gamma naught n level structure, your Fourier coefficients are indexed by integer powers of q. But if you change around the level structure, it can happen that you have powers of q with fractional exponents. And so similarly here, you need some nice level structure to make it really strictly true that the Fourier coefficients are indexed exactly by this data. Sometimes you might have some integrality issues or things like that. Okay. So the sort of main fact I want to impress on you about these Fourier coefficients is that they're highly arithmetic in nature. So they're not just a bunch of sort of random complex numbers. They have arithmetic structure to them. And here are two examples to hopefully help convince you of this fact. So the first example is Eisenstein series. So it's sort of well known in more classical situations that the Fourier coefficients of Eisenstein series are often particularly simple. And this is also true in this G2 setting. So there's a natural family of Eisenstein series, which correspond to quaternionic modular forms. And the eighth Fourier coefficient of such a thing is given by a zeta value, at least when A is maximal. So maximal here means maximal inside A tensor Q. So think like the ring of integers in a totally real cubic field, not an order in a totally real cubic field. And of course, this is the zeta value that would, for example, correspond to that cubic field. So that's already, I think, somewhat striking example, but it's of course specific to Eisenstein series. But more generally, it's known, at least in level 1, and in sufficiently large weight, that there's a basis of quaternionic modular forms with all coefficients lying in the cyclotomic field generated by all roots of unity. So this is a pretty recent theorem of Aaron Pollock, and to sort of give some context for this result, of course, this is true for this would be true for classical modular forms that you can always make a basis, in fact, with rational Fourier coefficients. But in this setting, it's a lot more surprising. So in the presence of holomorphic discrete series, you would prove something like this, typically using algebraic geometry and sort of geometric interpretations of Fourier coefficients. But here, there's no geometry in sight, and yet still the Fourier coefficients have this really quite strong rationality property to them. And it's expected to be true for more general levels, but it's currently known in level 1. Okay, so that's sort of the basic story of Fourier coefficients. This talk, more specifically, is about Gross's conjecture. So the setting for this is you should fix a classical cusp form on SL2Z of some weight k. and consider a certain functorial lift of this form called the Gan-Gurevich lift, which is a cusp form on the group G2. So this has been constructed by Gan-Gurevich under the condition that the central L value of f is non-zero, but it's expected to exist somewhat more generally. So this functorial lift, I'll tell you a bit more about where they come from later, but you should, for instance, you can characterize them by their Hecke eigenvalues being related to those of f in a certain way. And so Gross made the following conjecture about these Gan-Gurevich lifts, that if you look at their Fourier coefficients along maximal totally real cubic rings, the square of the Fourier coefficient is essentially an L value for f twisted by the two-dimensional Artin representation that corresponds to A. So here, this Artin representation, you should think about, for instance, if A corresponds to ring of integers in a totally real cubic field, you'd be taking the induction of the trivial from like the cubic field, the Galois group of the cubic field, the Galois group of Q, that has a two-dimensional, that has a one-dimensional trivial piece. Get rid of that. The remainder is a two-dimensional Artin representation. That's what you're twisting by. Now, structurally, this conjecture looks a lot like Wallis-Bourget's theorem on Fourier coefficients of modular forms for half integral weight, sort of in this different, more exceptional setting. So until recently, not much was known about this conjecture, but the first sort of major progress on it came in November last year, when Kim and Yamauchi proved this conjecture for the cubic rings that are of the form Z times ring of integers in a real quadratic field, and maybe also some orders in such things. So this is kind of a thin set within all of the possible cubic rings, but still quite a striking result. Is in particular, it gives you infinitely many Fourier coefficients. So what we'll be talking about today is Gross's conjecture when, in the special case when f is a CM form. And we'll see you can actually prove, essentially prove something very close to Gross's conjecture in this setting, not without the restriction on the shape of A. But you should sort of be warned that the formulation of the conjecture will have to change. And the reason for this is that CM forms are never level 1. And so in particular, this creates some complications in the theory of the Gan-Gurevich lifts. Okay, so any questions so far?
So in this result of Kim and Yamauchi for this A, what does the row A look like?
So row A here should be trivial plus the sign representation for like the quadratic character associated to f.
Okay, so does this L function have a pole? If you tensor by trivial, then it's just tensor by the quadratic character? No.
Yeah, so it's the L value of f times the L value twisted by the quadratic character.
Okay, I see. Thanks.
Yeah. Okay, so now I want to tell you the main result of this talk. So this so we're going, as I said, we're specialized in the case of CM forms. So these are associated to the data of a Hecke character of a quadratic imaginary field. And so now the level can be anything, but we still want trivial central character. And that's not a technical assumption that's expected to be necessary for the theory of Gan-Gurevich lifts. And we will assume that the L value of f, or equivalently of chi, is non-zero at the central point. So this is similar to really the same condition that was used in Gan-Gurevich's construction, and we also need it in order to construct the Gan-Gurevich lifts. And in this setting, instead of thinking of a single modular form that is the Gan-Gurevich lift, it's better to think of the space of sort of all of the Gan-Gurevich lifts. So that's some subspace of this automorphic forms on G2, which I'll tell you more about later. But in particular, without sort of, because we are allowing any level, there won't be a distinguished kind of new form in this space. Okay, so here's the statement of the theorem, which is currently work in progress. So the data you have to give me is for every prime dividing the level of your modular form, you need to choose your favorite cubic ring over ZL. And for any choice of local cubic ring and the local data of chi, there's a certain epsilon factor, which again, I'll say more about, but this is just some sort of local plus or minus 1 that you get from this data. And there's a global sign condition that the product of all of these has to be negative the global epsilon, sort of global root number of chi cubed. And under this assumption, the conclusion is that there exists a cuspidal quaternionic modular form in the space of Gan-Gurevich lifts, such that for those cubic rings A, which are maximal outside N, the norm squared of the Fourier coefficient is given by the L value that you expect when A is locally sort of the cubic ring that you chose as your favorite. And if it doesn't satisfy all those local conditions, the Fourier coefficient is 0. Okay, so sort of a few things to remark about this. One is sort of in the phantom case that you had a level 1 form, which is not actually possible. This condition would sort of not appear, right? Because this is only a condition at primes dividing the level. And then you would recover something that looks more like Gross's conjecture. And in general, as I'll explain, we think this formulation is essentially optimal for sort of getting something that looks like Gross's conjecture that takes into account the level. Any questions about the main theorem? Okay, so here's what I want to do for the rest of the talk. So first, I want to sort of go back and explain more about the theory of Gan-Gurevich lifts. And in doing so, I'll be able to explain the role of this epsilon factor condition that appears in the main theorem. Then I'll tell you about an explicit construction of the space of Gan-Gurevich lifts in the setting of CM forms. And using that explicit construction, I'll be able to explain to you the main ideas of the proof, and how you're able to explicitly calculate Fourier coefficients for these lifts. Okay, so to start off with the theory of Gan-Gurevich lifts, so this fits into sort of a more general framework of Arthur's conjectures, which let me just remind you of. So this is a typo. This should say G is a reductive group over Q. Apologize for that. So the sort of general picture of the Langlands program is that automorphic representations of a group G should correspond to something like Galois representations valued in the Langlands dual group. So here LQ is this conjecturally defined Langlands group, and Galois representations is here in quotes because LQ is supposed to be some kind of extension of the Galois group. But this picture was significantly refined by Arthur, who gave a more precise prediction for the discrete spectrum of the group G. And so his prediction is that you can write this as a direct sum over what are now called Arthur parameters of parts of the automorphic spectrum indexed by these psi's. So these parameters psi's are of the following shape. So they're maps into the dual group of not just this hypothetical Langlands group, but also the algebraic group SL2C. And these are supposed to satisfy the condition that when you restrict to the Galois part, psi is tempered, which is some kind of boundedness condition. And when you restrict to the SL2 part, psi is algebraic. So I want to just sort of give you picture of what this should roughly mean, the picture is that the more non-trivial the SL2C, the more non-tempered and degenerate the corresponding automorphic representations should be. So for example, when SL2C is trivial, these should correspond to tempered representations, which again is some kind of boundedness condition. And for instance, in the setting of GL2, the Langlands dual, of course, is just GL2 again. And you have only two options for psi on SL2C, right? It can either be trivial or non-trivial. And if it's non-trivial, then the Galois part has to map into the centralizer of SL2, which is just the center of GL2. So the data of psi is essentially the data of a character. And in this, so in this case, the corresponding automorphic representations are exactly those which are the determinant composed with an automorphic character. On the other hand, if psi is trivial on SL2C, then that corresponds to the sort of usual cuspidal automorphic representations of GL2, which are expected to be tempered by the Ramanujan conjecture. And actually, sorry, before I go on, let me just sort of remark here, this is a general sort of push and pull, that the larger the image of the SL2C, the smaller the image of the Langlands group. So you should expect that kind of the more SL2 there is, the less space there is for any kind of authentically cuspidal or Galois kind of data. Okay, so that's the general story. And the Gan-Gurevich lifts are supposed to come from this general story applied to the group G2 and the following kind of parameter. So the Langlands dual of G2 is G2 again. And here's a picture of the root system of G2. The parameters that we're interested in factor through these two commuting SL2s. You can see there's a long and short root SL2 that commute with each other. And we will take psi's that take the SL2C part to the long root and the Galois part to the short root. And by the way, I should maybe say that if you flip the roles of the short and long root, and so you send the SL2C to the short root, the corresponding automorphic representations are still very interesting, and they were also studied by Gan-Gurevich. But as it turns out, those don't involve any quaternionic modular forms. So that's the reason that the long root is kind of more arithmetically meaningful in some sense. So these are the shape of the parameters we want, and the sort of data that remains once you've decided that your parameter is going to have this shape is just the data of a cuspidal automorphic representation of PGL2. So that's because sort of what you get to choose is the map from the Langlands group to SL2C, and whatever the definition of the Langlands group is, such maps are supposed to correspond to, tempered maps like this should correspond to cuspidal automorphic representations of PGL2. So we can call the corresponding parameter psi sub tau, where tau is the automorphic representation. And we will specialize this story, of course, to the CM case. So tau is tau sub chi for some kind of Hecke character, giving rise to the CM form. And then the corresponding space of Gan-Gurevich lifts is defined to be this part of the discrete spectrum of G2, indexed by this parameter psi. Now, you might be kind of uncomfortable with this definition because Arthur's conjecture is conjectural. It's formulated in terms of this hypothetical Langlands group, which isn't known to exist. But in fact, the definition of this Gan-Gurevich space can be made totally unconditional. And the way you can do this is from the knowing tau and that you're constructing psi this way, you can read off what the Satake parameters are supposed to be for anything in this sort of part of the discrete spectrum. And I won't write down the recipe, but there's a general recipe for what those Satake parameters should look like that depends on tau. And so the point is that you can actually define this Gan-Gurevich space as just the direct sum of all automorphic representations, such that at cofinitely many places they have the Satake parameters you expect. So even though the motivation for this definition comes from Arthur's conjectures, you can make the definition kind of make sense unconditionally. And so Arthur has a description, a precise conjectural description for the psi part of the automorphic spectrum, which involves two kind of stages. There are local packets of local representations, and then there are global multiplicities, which tell you how the sort of automorphic representations are built up out of the local packets. So I want to explain for you this picture specialized to the case of these Gan-Gurevich packets, although of course it's part of this much more general recipe. So there are sort of two steps to the description. So first you have a local packet. So the local packet is a pi v plus and a pi v minus, where the local packet only depends on the local behavior of k and chi at that place of q. And these are defined so that pi v minus is actually 0 for cofinitely many primes. So actually almost everywhere you only have one choice in the packet, but finally many places you have two choices. And the Gan-Gurevich sort of part of the spectrum is supposed to be built up out of restricted tensor products of pi v pluses and pi v minuses. So you choose a sign at every place. And this global representation appears in the automorphic spectrum with multiplicity 1 or 0, depending on whether all the epsilons you chose satisfy a global sign this global sign condition involving the epsilon factor for chi cubed. And let me just pause for a moment to make sort of an editorial comment. I think one thing that's always really interesting about this field and kind of any examples of the Arthur multiplicity formula that are known is to see how arithmetic kind of conspires to make sure the multiplicity formula holds. So it's this sort of global multiplicity is in some ways the most subtle part of the conjecture, and it somehow seems that how did nature know that it had to make the multiplicity formula true, but it always seems to find a way to do it. And as an example, in this particular context, if you kind of trace back the multiplicity formula to see where you can track it to, where is the obstruction, the sign obstruction really coming from, it really comes from the local global obstruction for the existence of Hermitian spaces. So if you choose Hermitian spaces of the same dimension at every place of Q, and you want them to sort of glue together into a global Hermitian space, there's a sign obstruction. And the sort of conspiracy aspect of this is that the multiplicity formula is about G2. There are no Hermitian spaces involved, but somehow when you go to try to construct these automorphic representations, you have to use some Hermitian spaces in the construction, and that's where the sign condition makes its way into the formula. So that's sort of the representation theory prediction for the structure of this space of Gan-Gurevich lifts. And now let's relate this back to the theory of Fourier expansions. So if you take one of these pi's, which are restricted tensor products of things in the local packets, you will find that you can only have a quaternionic modular form if the Archimedean epsilon factor is -1. At infinity, you need to take pi infinity minus, not pi infinity plus. And that's exactly because pi infinity minus is a quaternionic discrete series, and pi infinity plus is not. So at infinity, your hand is forced by wanting it to be a quaternionic modular form. On the other hand, there are some obstructions to supporting Fourier coefficients at primes that divide the level. So if you look at the eighth Fourier coefficient of such a global phi, it will have to vanish unless the epsilon at L that you chose is a certain value that depends on the local behavior of A and chi. So in particular, there's a local notion of these Fourier coefficients, and if you fix A locally, only one of pi v plus and only one of pi L plus and pi L minus can support that Fourier coefficient. So if you want to sort of see an interesting eighth Fourier coefficient, you will need the following sign condition, that the product of the local signs at places dividing n is minus the product of is minus the global epsilon factor of chi cubed. And that's because the Archimedean component contributes a -1, and then from the multiplicity formula, you get this. So to return to the formulation of the main theorem, hopefully it's now sort of more reasonable that this epsilon condition is appearing. So this is exactly the condition you need, or certainly this condition is necessary to have the conclusion. And we've sort of come to the opinion that this is the best that you could hope to do in terms of a formulation of Gross's conjecture that takes into account the existence of these sort of local, non-trivial local package structures. So yeah, so that's the main result. Any questions at this point before I go on? Okay, cool. So the next thing that I want to explain is the construction of the space of Gan-Gurevich lifts. So where it actually comes from and why we'll be able to work with it explicitly. So the construction is in the setting of exceptional theta correspondences. So a theta correspondence, very generally, is a construction that lets you transfer automorphic representations from one group to another group if the groups are in a certain relation called being a dual reductive pair. So it's a general construction of automorphic forms, automorphic representations on one group from another. And being a dual reductive pair means that you can embed them as mutual centralizers inside a larger group G tilde, where G tilde is a group that has some kind of appropriate theory of theta functions on it, which are special automorphic forms that you'll be able to use as a kernel. So the actual construction of the theta correspondence just involves taking this theta function, pulling it back, and using it as a kernel. So you integrate an automorphic form on G against it, and you get an automorphic form on H. So this story of theta correspondence was first studied in a classical setting. And here the groups G tilde are all symplectic groups. And the dual reductive pairs that you get roughly fall into two cases. One is symplectic orthogonal, and the other is unitary-unitary. And in both of these cases, notice you have the flexibility of any size groups that you want on both ends. So that's the classical story of theta correspondence. But as it turns out, there are also some exceptional theta correspondences. So in these, the group G tilde is an exceptional group, E6, E7, or E8. And the dual reductive pairs always have one factor of G2, and the other factor is rank 2, rank 3, or rank 4. And so on the one hand, you can see that this theory is somehow more restrictive. There's less flexibility in the kinds the different ranks of the groups that you can use. But I think it's also pretty plausible looking at this list to see that this could be very useful for constructing automorphic forms on the group G2. And in fact, the way Pollock proved that fact about the Fourier coefficients was realizing automorphic forms on G2 as theta lifts from F4. So it's it's a useful lens for looking at forms on G2 in some kind of explicit way. In fact, what's relevant for this talk is actually not the dual pair that I had written down here, but actually sort of a quasi-split form of it. So instead of PGL3, we'll use PU3, and instead of E6, you have a quasi-split form of E6. And yeah, I should say all of these dual reductive pairs can have sort of quasi-split or inner form kinds of incarnations. Okay, so the construction of Gan-Gurevich lifts using exceptional theta correspondences. So that started with the work of Gan and Gurevich, obviously. And they constructed their lifts using the theta correspondence to PGSP6. So they started with a cusp form on PGL2. They transferred it to PGSP6 in some kind of complicated way that is not actually a theta correspondence, but some other kind of way of moving from here to there. And then this gives them a very non-tempered, very degenerate cusp form on PGSP6 that sort of has the only cuspidal data involved is sigma, but it's some kind of very, very non-tempered thing. And then you theta lift that to the group G2. Now, what we're doing is a different approach that only works for CM forms. So here, instead of theta lifting from PGSP6, we'll theta lift from the group PU3. And I should say that this you can see sort of you can prove that this will not work to construct anything that's not CM. This is special to the CM setting. And the things that we're lifting on PU3 are also themselves pretty simple to understand. They are themselves theta lifts from the group U1. And the way the data of chi gets in there is actually something to do with some auxiliary data in defining the theta correspondence. So technically, you're lifting the trivial representation of U1. But that's not so important. What matters is just that these, both of these steps are in red are quite simple to understand. So the main advantage of the red path as opposed to the black path is that it's easier to understand the packet structure from this method. So Gan and Gurevich were able to prove that they had that the lifts they got were non-zero, but they weren't able to sort of fully understand the intricate packet structure. Whereas here we can get it because we understand the packet structure of these non-tempered things that we're lifting from PU3, which, by the way, are sometimes called the Howe, Piatetsky, Shapiro cap forms on the group PU3. And okay, so that's how the Gan-Gurevich lifts are constructed explicitly. And sort of what remains is that I want to tell you how you can use that construction to calculate their Fourier coefficients and get this version of Gross's conjecture. So first, let me just say more about what Fourier coefficients really are, because I didn't actually give you a definition of them. So here's again the picture of the G2 root system, and circled in red is the unipotent radical of the Heisenberg parabolic. So we're looking at Fourier coefficients with respect to this parabolic. So here's the Levy factor m. It's just GL2, and in the unipotent radical, you have this highest root z, which is the commutator subgroup, and you also have sort of a four-dimensional remaining space of the unipotent radical. So if you think about the characters, the adelic characters of n, these will be indexed by quadruples of four rational numbers. And so the rationality, so it's four because of this four-dimensional group mod commutator, and rational because you're only interested in characters that are trivial on the rational points of n. And you can set up this bijection, and I'll call the corresponding character psi sub lambda. So now if you take any, well, this definition makes sense for any modular form on or any automorphic form on G2, but we're interested in it for quaternionic modular forms. We define one defines the lambda Fourier coefficient of phi as essentially the integral along this unipotent radical against psi lambda inverse of n. So you're just picking up the psi lambda isotypic piece. The dot over the equal sign here indicates that there's a factor in front that I have not written down, which is rather interesting. It involves some Bessel functions, but I didn't want to write it. But you need that factor in order to actually make what you get the sort of the correctly normalized arithmetic number, or sort of arithmetic object, rather than just a random complex number. Okay, so these are the Fourier coefficients that we're interested in. But this is not the story that I told you in the beginning, because I told you that Fourier coefficients were indexed by totally real cubic rings. So let me explain how you get from this more idyllic picture to that one. So so as I said, this requires something about the level of phi. So in particular, we're going to specialize to phi being invariant by the z hat points of this Heisenberg parabolic. Now, this means two things. So first, it means that the lambda Fourier coefficient will be supported on quadruples which are actually integral, not just rational. And the reason for that is that if you will only pick up a Fourier coefficient if psi lambda is trivial on n of z hat, which corresponds to lambda being integral. And so that uses the invariance by the unipotent radical, but you still have the invariance by the levy. So there's this extra symmetry that comes from the action of the levy. So as it turns out, if you look at the orbits of phi over the relevant part of the levy, which is isomorphic to GL2Z, the orbits of these lambdas under the action of the levy exactly correspond to cubic rings. So from a quadruple of integers, you can cook up a cubic ring through a certain recipe, where you take z cubed and you define some multiplication law on it that's determined by the quadruple. And yeah, so as it turns out, the equivalent, the sort of orbits of lambdas under the levy are exactly captured by the cubic rings. More generally, if lambda is just rational, not integral, the same construction will instead give you a cubic algebra over the rational numbers, where just now, because the multiplication law doesn't preserve the integral structure, there might not be a corresponding ring. Now, the final piece of the puzzle to relate this to what I explained, to sort of what picture I gave at the beginning of the talk, is that you only get totally real things. So these Fourier coefficients will actually vanish unless E lambda is totally real. The reason for this is similar to the reason why for classical modular forms, you don't have any negative powers of Q in your Fourier expansions. So there's some kind of boundedness condition that phi will have to fail if it has a non-zero Fourier coefficient for something that's not totally real. So that's a somewhat more subtle kind of Archimedean calculation. Okay, so now we've sort of recovered the story with the totally real cubic rings. And now let me explain how you can actually compute these Fourier coefficients. So there's a very general principle in the theory of the theta correspondence, which is that periods for a theta lift often reduce to periods for your original automorphic representation. And you can kind of picture why this would be true. So the theta lift is defined by integration against some kernel. And if you then take a period of what you get, you have a double integral. So there will often be a way to interchange the integrals and get and ultimately reduce to something involving your original automorphic representation. And in this case, we're looking at Fourier coefficients, which are themselves periods. They're integrals over unipotent radical. So if you kind of carry out this process, what you will find is indeed that the Fourier coefficient of one of these phis in the space of Gan-Gurevich lifts is related to some torus periods on PU3. So here E is the totally real cubic étale algebra that corresponds to some lambda. So I'm allowing phi to be any level, so I'm thinking of lambdas rather than A's for the moment. And you can embed so you can embed E into the 3x3 Hermitian rational matrices. And the reason that's possible is that E is totally real, right? So Hermitian matrices always have real eigenvalues. So this is necessary to do such a thing. And you can imagine that if you have this embedding from E into Hermitian matrices, you get some kind of torus embedding inside. So some torus corresponding to E living inside PU3. And then that's sort of the subgroup that you're integrating along, and the thing you're integrating is the form that you're theta lifting from PU3. So this is some automorphic form on PU3, which are what we were calling the Howe PS cap forms. Okay, so you can unfold to these kinds of torus periods, and then you have to compute those. And for these, you again are in luck because rho is itself a theta lift. So these rhos are also pretty explicitly constructed. And if you sort of again try to just directly calculate this integral, you'll get a formula that looks something like this. So you can prove that the norm squared of this torus period is essentially the L value of f chi twisted by this two-dimensional Artin representation corresponding to E from before, times you also have the L value of chi itself, and then you have some power of discriminant as well. And I should point out here, this is exactly why we only are able to do anything when L1 half chi is not 0. Otherwise, we would actually just get that all of the Fourier coefficients are 0. So we wouldn't have constructed anything interesting. Okay, so hopefully from what I've said, it's kind of plausible that you could prove a formula that looks like this. So norm squared of the Fourier coefficient is the L value you're interested in times L1 half chi times this discriminant factor, and then times a product of local integrals, norms of local integrals. And the reason those appear is those two tildes here and here were both kind of doing a lot of work. They were hiding a lot of sort of local subtleties that happen because of your possible choices of test functions. So you can, if you track that through, you'll get certain local integrals that depend on the local if phi is factorizable on the local part of phi, and on what Fourier coefficient you're taking. So to finish the proof, we need to be able to evaluate these local integrals. So first, the Archimedean setting. This is where you get the rest of the discriminant factor that you expect. That depends on the weight. And I'll mention the way you can calculate this Archimedean integral uses some really nice work of Aaron Pollock, which tells you how to sort of work very explicitly with Whittaker models for quaternionic discrete series and related representations on exceptional groups. So in this case, we're using that for the group E6, where the theta lift is coming from, and it's only sort of thanks to this work that we're able to work explicitly at infinity and really get a number out of this Archimedean integral. On the other hand, these integrals at non-Archimedean places seem quite hard to compute in general. So there are sort of two sort of relevant parts. So first is the primes not dividing the level. And we're able to show here that if you take phi L to be the spherical, so like a standard spherical test vector, you will get a local integral that's exactly 1 if your lambda kind of locally corresponds to a ZL cubic ring that's a maximal order in a cubic étale algebra. If it was a non-maximal order, we do not know how to compute this integral. It seems very hard, and that's why in the theorem, and I mean also in Gross's conjecture, you're restricting to things that are maximal, at least outside n, because otherwise, yeah, it's not really clear what you should expect for the non-maximal things. And so that takes care of primes not dividing the level. For primes dividing the level, well, in this case, we're allowed to be pretty flexible about what our test function is. So we show that you can kind of cook up a test function in such a way that the local factor, the local integral will be the indicator function of lambda corresponding to any fixed kind of local ZL cubic ring that you might want to choose. And so these aren't sort of natural test vectors, but that maybe shouldn't surprise you because these local components are kind of, in general, they're like very non-tempered supercuspidal representations of G2. Maybe it's not surprising that there's no sort of good local test vector to pick a priori, but you can pick one that's well suited to these kinds of Fourier coefficient calculations. Okay, so with these, that's essentially the proof of the theorem. You just you put these together and you'll get the calculation of the Fourier coefficients that I displayed before. Okay, and I will stop there. Thank you for listening.